Texture synthesis is one avenue of image-based rendering that has grown in recent years, as it makes it possible for researchers to recreate the physical world from a small set of sample images, as opposed to from scratch. The goal of texture synthesis is to algorithmically generate a texture from an image that captures the visual characteristics of the image, but is not identical to the original, in order to create a larger digital image from a smaller one. These examples on the screen show a sample texture and a resulting image grown from these samples. I read through a couple of papers in order to implement texture synthesis, most namely texture synthesis by non-parametric sampling by Afros and Lung. The paper depicts a method based on spatial locality, in which a new image is grown outwards pixel by pixel from an initial seed. The sample image is queried to find all similar neighborhoods to a given pixel in order to fill in a similar pixel elsewhere in the image. As seen on the screen, the image on the left-hand side of bricks shows all the similar neighborhoods to the section boxed on the right-hand side so that the blacked-out regions can be filled in. This is the algorithm that I base my implementation off of. The texture synthesis by non-parametric sampling algorithm, at a high level, grows an image outward from a seed one pixel at a time by finding pixels with similar neighborhoods in the input image. To synthesize a new image from scratch, the algorithm begins with a 3x3 seed of the input. The only parameter that the user needs to specify is the window size. I tested out different window sizes and timed how long my implementation ran on each of these, and this information is shown in a later results slide. While the image is not filled or there are still black pixels, the algorithm gets a list of all the unfilled pixels with filled pixels as their neighbors that is sorted by decreasing number of filled neighbor pixels. Then, for each pixel in this list, in sorted order, the neighborhood window or region of specified dimensions centered at the given pixel in the output is extracted. For each of these pixels, the algorithm finds the best corresponding pixels in the input image by comparing the neighborhoods of both. One of the best matches is randomly selected, and if the error is below some maximum error threshold set to 0.3 in my implementation, the value of the pixel in the output is set to be the value of the corresponding pixel in the input. If no progress is made in one full iteration of the unfilled neighbors, the maximum error threshold is increased by 10%, and the process is repeated. To identify a matching pixel, the algorithm iterates through all the pixels in the input image, comparing their neighborhoods to the neighborhood of the pixel from the output image. The sum of square distances is calculated for all filled pixels in the neighborhood from the output image, with each square distance weighted based on a two-dimensional Gaussian. A match is considered any pixel from the input that results in a sum of square difference that is below a predefined error threshold, which I set to 1.1 times the minimum square distance. The algorithm purposefully determines a list of matches, and then randomly selects a match from it, as opposed to simply returning the match with the lowest sum of square distance, and this is to incorporate an element of probability, which ensures that the resulting image is not homogeneous. However, note that with the greater window radius, the homogeneity increases. The results here are from running my algorithm on a wood desk, with the rectangular part blacked out. The wood texture is synthesized in that hole, and as you can see, it works pretty well in recreating an accurate looking wood texture within those blacked out pixels. In conclusion, my texture synthesis implementation explores ways of finding a best match for a pixel in texture synthesis by varying window sizes and the error threshold for which pixels are chosen to fill a hole in the image. I experimented with both of these parameters and timed how long the procedure took to synthesize a texture. Larger window sizes were quicker, since a match for a pixel was found with less iterations. However, increased speed sacrificed randomness in the results, which is a necessary quality of stochastic textures. These two properties must be balanced in order to create a natural-looking texture sample from a small seed, which is the challenge of irregular patterns. Extension work to this idea includes applying texture synthesis to a video and fluid textures, to see how time extensive these processes are and how window size plays a role in their algorithm. Thank you.